Welcome. In first lecture of this section, we learned how to estimate, how to size a system from scratch using nothing but arithmetic and a few reference numbers. And then in the second lecture of this section, we learned how to commit, how to define the formal reliability contracts that govern how a system must behave. And now in this lecture, we do the hardest part. We translate and requirements is not in architecture, something that you have to translate the requirement into architecture. Similarly, a user story is not a system design. So the gap between what a stakeholder says they need and what an engineer needs to build is enormous. And most systems fail because nobody bridges that gap deliberately. So they fail because someone hears that the search should be fast, and they made a technology choice without understanding what fast means, for how many users it should be passed, for how many times it should be, for how many items it should be passed, and at what percentile. So these metrics are missing. So the architect's job is to be the translator, to take an ambiguous human requirement and turn it into a precise, defensible architectural decision. So in this lecture, I'm going to give you the tools to do that, and we are going to cover how to classify requirements and how to use architecture decision records, and I will share a 5-question decision framework and a real Netflix case study as well. So by the end of this lecture, you will have a complete workflow from reading a requirement to making an architectural decision you can defend to anyone in the room. So let's build that workflow. So let me show you the translation problem in action. Let's say a product manager walks into the room and says users should be able to search the product catalog instantly. That sounds clear, does not it? But it is not clear. As an architect, when I hear that sentence, I immediately have 4 questions. And each question has a completely different answer that leads to a completely different architecture. So here we have question number 1. What does instantly mean? Does it mean 100 milliseconds at 99th percentile? Or does it mean 500 milliseconds? So the difference between those two targets completely changes whether I can use a standard relational database or I need Elasticsearch or a specialized search cluster. Then in question number 2 that I have, how large is the catalog? 1000 products? That is trivial. A simple index column in Postgres handles it. But it is 100 million products, so that is completely different problem, requiring sharding and inverted indexes and indicated search infrastructure. So you know that each question should be answered so that you can take better decision while choosing a particular architecture. Then we have the question number 3, and that is, what kind of search? Does the user type exact product names, or do they type partial words and expect results to match? So do they need filters by price, by category, by rating, and do they expect typo tolerance? Each one of those is different algorithm with different infrastructure requirement. And then we have question number 4, which is, how many user search simultaneously? This is the estimation we did in the first lecture of this section. QPS determines whether a single search server handles it or whether we need a distributed search cluster with load balancing. So this instantly is not a requirement, it is an aspiration, and your job as an architect is to turn this aspiration into 4 or 5 specific measurable questions and then to answer them. So the process of turning instantly into clear measurable system goals like fast response time under heavy load, so that is software architecture. Before you can translate a requirement into an architecture, you need to understand what kind of requirement it is, because different types of requirements drive completely different architectural decisions. And we already talked about the different type of requirements earlier in the course. We saw that there are functional requirements and non-functional requirements and some quality attributes as well. So but we didn't cover all these type of requirements. So there are 4 types of requirements, and let me walk through each one of them. The first one is a functional requirement. You can see over here on the left hand side, these describe what the system does, and user can search, checkout creates an order, admin can revoke access. So these requirements tell you what your APIs need to expose and what your domain model needs to represent. So they define the surface area of your system. Then we have the quality attributes, and this is the LATs, ILITIES, like availability, scalability, reliability, and even performance. Even performance is not having LAT, but performance is also quality attribute. So these describe how well the system does what it does, right? So these are the requirements that drive your technology choices. When you choose PostgreSQL or MongoDB, when you decide to use message queue, when you add a cache layer, so you are responding to quality attribute requirements, and these are the most architecturally significant requirements you will encounter. And then we have the constraints. These are the non-negotiables and the things you cannot change. Must run on AWS Go Cloud, right? So that is one constraint, because the customer is a government agency and must comply with GDPR, because your user are in Europe. Cannot add new databases because the company already has an Oracle license and an operation team that only knows Oracle. So these are some constraints, and constraints narrow your solution space, sometimes dramatically. The architect who ignores constraints will design a perfect system that nobody can actually deploy. And then we have the assumptions. These are the most dangerous. An assumption is something you believe to be true but have not verified, like traffic peaks on weekdays. Users are temporarily using mobile phone. The data is mostly used, not they are mostly written, not read. If your assumptions are wrong, so your architecture will fail in ways you cannot predict. Write your own assumptions down and explicitly mention that this assumption can happen, and then verify them. So before you build, not after you launch, you have to write down all your assumptions. Let me try again. Write down every assumption explicitly and then verify them before you build, not after you launch. When you receive a requirement, your first job is to classify it. Which of these 4 types is it? And that classification tells you what architectural decisions it derives. Alright, now I want to introduce one of the most valuable habits I have built in my career, and it is called an architecture decision record, ADR, right? So an ADR is a short document no longer than 1 page that records a single architectural decision, not all decision, not a design document, one decision and 1 page. So look at the example on the left. Let me read through it. We have the title. So you can see over here ADR 042, and then we have the title, use Elasticsearch for product search. Notice it is numbered. You track your ADRs like you track code commits. Then we have the status, and it is accepted. Other statuses might be proposed, deprecated, or even superseded. Then we have the context, and the context we have the text like product search must handle 50,000 requests per second with typo tolerance. Faceted filters across 80 million SKUs. So this is where you connect the requirement to the numbers, and this is where our lecture 1 of this section feed directly into our this lecture, right? And then we have the decision over here. You can see. So adopt Elasticsearch 8 with a 6 shared primary cluster, and then we have the specific actionable unambiguous. Let me try again. Then we have the decision adopt Elasticsearch 8 with 6 shared primary cluster. So this decision is specific, actionable, and unambiguous. Then we have the consequences. If in case you want to take a decision, so what could be the consequences of that decision? So we write down that consequences over here. Like in our case, search latency percentile 99 under 80 milliseconds. A percentile means if 100 people use search, 99 out of them will get results in under 80 millisecond, and only one might be slower. So we achieved our SLO, and there is new operational complexity. We need a dedicated SRE with Elasticsearch expertise, right? The last field is alternatives, and it is the most important field in the entire document. It proves that you thought about the decision and that you didn't just pick the first thing that came to your mind. So now look at the 4 reasons on the right hand side. ADRs prevent relitigating decisions. Every team has that new engineer who joined 6 months after a decision was made and says, why didn't you just use X? So within ADR, the answer is over there, and we considered X. Here is why we rejected it, and the conversation ends before it starts, right? So the ADRs force trade-off thinking. The act of writing the alternatives sections makes you think harder. So you cannot write we rejected PostgreSQL because of performance at scale without actually validating that claim, right? And ADRs connect requirements to code. So when the business changes direction 6 months later, so you can look at your ADRs and know exactly which technical decisions were made in response to the old requirements and which ones need to be revisited. And ADRs build institutional memory. Code tells you what was built, but ADRs tell you why. These documents survive team turnover. They are the archaeology of your system. Start with ADRs today, even for decision you have already made. Alright, now I want to give you a framework, 5 questions. Every time you face an architectural decision, ask these 5 questions in order. Question number 1 is, what is the dominant quality attribute? Every system has one quality attribute that matters more than others. So for banking system, it is consistency. A wrong balance is worse than unavailable system. For social media feed, it is availability. Being down is worse than showing stale posts. So for streaming platform, it is throughput. The system must deliver video at scale. Identify the dominant quality attribute first. It will guide every subsequent decision. Then question number 2 is, what is the read-write ratio? So you calculated this in the first lecture of this section. If your system is read heavy, more than 10 reads per write, so you invest in caching, read replicas and CDN, right? But if it is write heavy, so you invest in event sourcing, message queues, and append only log structures. So these are very different architectures. So the ratio is the dividing line. Then question number 3 is, what is the data model structure? So the shape of your data should determine your database choice, not other way around. If your data is highly relational with complex joins, a relational database is the right tool. But if your data is hierarchical or document shaped, so document store fits better. Time series data belongs in a time series database. highly connected data like social graph belongs in a graph database. So let the data choose the storage engine for you. And then we have question number 4. What is the failure tolerance? So the RFO recovery point objective is how much data can we lose if the system fails for 5 minutes, for 1 second, or maybe 0. So then we have the RTO, which stands for recovery time objective. How long can we be down while recovering, right? So 1 hour, 5 minutes, these two numbers completely define your backup strategy, your replication topology, and your failure architecture. Then we have question number 5, which is what is the team capability? This is one question that most architects had to ask, but it is the most honest question on this list. The best architecture your team cannot operate will perform worse than a simpler architecture that your team understands deeply. Operational complexity is a real architectural constraint. A junior team deploy microservices across Kubernetes will have worse uptime than a senior team running a well-designed monolith. So be honest about this. Design for the team you have, not the team you wish you had. Now let me show you the translation framework and action on one of the most studied architecture transformations in the history of the software industry. And this is Netflix 2008. They have just committed to moving everything to Amazon Web Services. And then someone in the leadership asks the question like, what happens when AWS has an outage? Because AWS will have outages. Every cloud provider does, and if Netflix goes down when AWS goes down, so that is catastrophic single point failure, and then millions of customers cannot watch movies, revenue stops, trust is destroyed. So that business questions become an architectural requirement. Netflix must remain available during AWS outages. So let us trace how that one requirement became 5 architectural decisions. So first decision, there was multi-region active deployment. So instead of one primary region with a backup, Netflix deployed in multiple AWS regions simultaneously, all of them serving traffic. If one region fails, traffic automatically routes to others. No manual intervention, no waiting, everything was automatic. Then we have the second decision, and it is circuit breaker pattern. This is what Hystrix implements. Hystrix helps system stay working even when some parts fail. The idea is simple. If a backend service starts failing, stop calling it, right? Immediately. Do not let the failure cascade through the entire system. Instead, serve a degraded response, maybe without personalized recommendations, but keep streaming. A degraded experience is infinitely better than a completely failed one. Then we have the third decision, and that is eventual consistency via Cassandra. So Netflix realized that some data like your watch history, your recommendations, does not need to be perfectly consistent in real time. They chose Cassandra, which accepts writes to any node and synchronizes across replicas eventually. So movie metadata might be 200 milliseconds out of data, but your system stream never blocks waiting for a database to synchronize. Then we have the fourth decision, that is chaos engineering. This is the most counterintuitive one. Netflix built a tool called Chaos Monkey that deliberately kills random servers in production on purpose, right? During business hours, the logic is brilliant. If you need to be resilient to failures, the best way is to build that resilience is to practice surviving failures. You cannot be surprised by something you regularly rehearse, right? Then we have the fifth decision, and their own CDN Open Connect combined with microservices, and today 90% of Netflix traffic never reaches their origin servers. It is served directly from edge nodes installed inside internet services provider around the world. So the origin is completely decoupled from the scale problem. And then we have the fifth question, that is so let me try again. So 5 requirements and 5 decisions, each one traceable back to the original question, what happens when AWS has an outage. So that traceability from business concern to architectural choice is what separates architecture from engineering guesswork. Alright, now let's talk about the quality attributes. Even though in the start of the course I've already discussed some of the quality attributes, and if you remember I gave you an example of a door where we focused on security, and whenever you focus on security, so you have to compromise on convenience. And I give you an example of a door where the door had a lot of locks, right? So if you want to make it secure, you can add a lot of locks on a door, but you have to spend a lot of time each time you want to open the door. So by doing this, you can making the door secure, but you have to sacrifice the convenience of the door. So there is a phrase which I want you to remember for the rest of your career, and that is that there is no free lunch in architecture. Every time you choose one quality attribute, you are giving something else up. So the architect who does not understand this will make promises they cannot keep. So let me walk through this trade-off table, and you can see the row number 1, the consistency. If you choose consistency, so you sacrifice some availability. This is the word of banking and financial systems. If the balance in your account is wrong, so even temporarily, that is catastrophic failure. So we design for consistency first, and availability is secondary. If the database needs to lock a record to ensure consistency, that is acceptable. Being slightly slower is better than being slightly wrong, right? And then you can see the availability. If you choose availability, so you sacrifice some consistency. This is the word of social media. Twitter would rather show you a feed that is a few hundred milliseconds out of date when there's no feed at all, right? So being eventually consistent is fine. Being completely unavailable is not. Then we have low latency reads. If you choose low latency reads, you sacrifice write complexity. This is the CQRS pattern, command query responsibility segregation. So you pre-compute your read models so that reads are instant, but every write now has to update multiple read models, and writes become more expensive, reads become nearly free, and this is the right trade-off for read heavy systems, right? And then we have the simplicity. If you choose simplicity, you sometimes sacrifice raw performance, and a well-structured monolith with in-process calls will often outperform a naive microservices architecture where every operation requires multiple network calls. So simplicity is underrated in our industry. And then we have the scalability. If you choose scalability through sharding, splitting a large database into smaller parts so it can handle more data and user efficiently, then you will sacrifice the ability to do cross-shared transactions. This is one of the most painful trade-off in distributed systems. You get horizontal scale, but you lose the ability to automatically update the data that lives on different shards. So this forces you to design your data model around your shared boundaries. And none of these trade-offs have a universally right answers. The right answer depends on your dominant quality attribute, which is why the question 1 on the previous slide is always first. So the architect's job is not to find the perfect solution. It is to choose the right trade-off for this system at this scale for these users with this team. So make that choice consciously and document it in ADR and then own it. Alright, now let me bring everything together. This is the complete workflow that includes 6 steps, and every time in this order, right? So step number 1 is gather, and before any architecture discussion happens, collect all 4 types of requirements, like functional requirements, quality attributes, constraints, assumptions. So write them down. If you have not done this, you are not ready to make architectural decisions. And then we have step number 2, and that is the estimate. Use the 3-step framework from our lecture number 1 of this section to calculate your QPS, your storage, your bandwidth, and now your architecture is anchored to real numbers, not intuition, right? And then we have step number 3, which is to define SLOs. Turn your quality attribute requirements into specific measurable commitments, like availability, latency, durability, correctness. So use the formula from our lecture number 2 of this section and calculate the SLOs, which you can use later on, and these SLOs become the acceptance criteria for your architecture. Then we have step number 4, which is to identify the dominant quality attribute. Look at all your SLOs and requirements and ask, if we could only optimize for one thing, what would it be? So that answer shapes every major decision that follows. And then we have step number 5, which is decide. Apply the 5-question framework. What is the read-write ratio? What is the data structure? What is the failure tolerance? And what is the team capability? So let the answers drive your technology choice. Then in step number 6, we have record. So write the ADR, document the context and the numbers from your estimations, the SLOs from step 3, the constraints from step 1, and document the decision. Document what you considered and rejected, number it and store it with your code. So now look at the 3 golden rules over here. Never decide alone. Architecture made in isolation will have blind spots. Bring your team, bring the people who will build it, operate it, and use it. So their perspectives will catch things you cannot see alone. And then we have document the why, not just the what, right? So in 2 years, nobody will number why you choose Cassandra over Postgres. But if you wrote an ADR, so it's right there, and the reasoning is preserved. And then revisit regularly. Requirements change, scale changes, right? Teams change. An architecture decision there was correct in year 1, maybe wrong in year 3, right? So review your ADRs at least once a year and mark outdated ones as superseded. Make new decisions with new reality. This workflow is not glamorous. It is not part of the architecture that gets conference talks, but it is the part that determines whether systems succeed or fail. So this is the craft. Alright, now it's your turn, and here is your action item, and I'm going to be direct with you. This one is not optional. Go to your current project right now today and pick any architecture decision that was already made. It does not have to be a big one. It could be as simple as we choose PostgreSQL as our database. That counts, right? Now write an ADR for it. Fill in the context, like why was this decision needed, what were the requirements driving it, what were the numbers, and then fill in the decision, like what exactly was decided. Be specific. Then fill in the consequences. What did you gain, what did you give up, and then fill in the alternatives, like what else did you consider, why did you reject those options. And when you are done, Share it with one colleague. Ask them one question. Does the reasoning make sense? Is it clear why this decision was made? So, if they say yes, you have written a good ADR. If you struggle to fill in the alternative section, if you cannot remember what else you considered, so that is a sign that the original decision was not made carefully, and that is information. It tells you where to focus, right? So the alternatives section is the honest part. It is the part that proves your thoughts. An ADR without alternatives is just a journal entry. An ADR with well-reasoned alternative is professional architecture documentation. Start this habit today. Write one ADR this week and then another next week. Within 3 months, this will be automatic. And in 5 years, you will have a library of documented decisions that will make you one of the most valuable architects your team has ever worked with. With this, our current section comes to an end, and applying the knowledge of this section, you can now estimate any system, define its reliability contracts, and translate its requirements into defensible architectural decisions. Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So, if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.